Integration is probably the most challenging part of elementary calculus. We do have some dictionary, and I'm going to assume that you know it, but unfortunately the grammar is rather poor. There is just linearity, but there is no product rule, no quotient rule, and no chain rule, unlike the case of derivative. So what we have instead is some methods and a lot of tricks. Now the basic methods, they are quite simple, and there is just 3 of them, so that looks easy. But the hard part is recognizing which method to use and how to apply it properly. And that's exactly the topic of this series of videos on integration. When we see an integral, we look at a function in it, and then we compare it mentally with other functions that we saw before, with some other integrals that we saw before, and we try to fit this given integral into a suitable box. And then we apply the appropriate method. And that's something that needs practice and experience. Now, the easiest method to recognize is the partial fractions decomposition, and we will dedicate this video to it. And the other 2 methods, substitution and integration by parts, they will have their own videos. So, let's start with a simple example. When I see an integral like that, I say, okay, I can see a ratio of polynomials, so I'm going to use partial fraction decomposition. Step 1, I look at the denominator and write it as a product of linear factors, or quadratic if necessary. Well, it's already done. That's wonderful. So let's go to step 2. We set up the partial fractions. For each factor in the denominator, we create an appropriate partial fraction. Sometimes we have to do more fractions, but not here, so let's not talk about it yet. We add them, so the first one, here is the second one, and here is the third one. Now in the numerators, we should put some numbers, but we don't know which ones yet. So we use letters, and traditional choice is to use uppercase letters. So that's the general setup for this particular ratio of polynomials. Now the heart of the approach is to find A, B, and C, and there are several possible methods for them. Let me start with one which doesn't have an official name, probably, as far as I know, but I call it multiply out and compare trick. And it goes like that. We look at it and we say, what do we really want? Well, we actually want this ratio, or this expression, to be equal to this expression. So I write it down, and I treat it as an equation. Now, when I see an equation like that, my first feeling is that I would like to get rid of fractions. So I'm going to multiply both sides by the common denominator, which is actually here. So this should be easy. I multiply, and on the left I get 3 minus 9x. And on the right I'm multiplying by this group, and there is always something which cancels, which makes it very nice. So A is multiplied by x minus 2 and x plus 1. Then there is B multiplied by x minus 1 and x plus 1. And finally C is multiplied by x minus 1 and x minus 2. Now comes the multiplying out trick. I multiply out all these groups. And what do I get? There will be x squared multiplied by a. Minus 2x plus x is minus x. And again multiplied by a. And finally, minus 2a. The next group, x squared multiplied by b. And this is actually the famous formula, a minus b times a plus b. So I can see right away that there will be minus b. And finally, cx squared minus 1 minus 2 is minus 3cx and plus 2c. Now I'm going to rearrange it so that there is polynomial on the right and a polynomial on the left. Now here I'm going to make a little psychological trick. I will write it as 0 times x squared minus 9 times x plus 3. That's the traditional form of a second-degree polynomial. On the right, I can see x squared. How many times? A plus b plus c. It pays to be systematic. Okay, x times. Where is x? Let's hunt. Over here, minus a, minus 3c. And finally, the absolute term. Minus 2a, minus b, plus 2c. So you could call this the hunting stage. Okay, I can see a polynomial on the left, a polynomial on the right, so now is the comparison stage. I can see x squared 0 times, so this number should be 0. I can see x negative 9 times, which gives me another requirement. And finally, the absolute term should be 3. And we obtained a system of 3 equations with 3 unknowns, so we should be able to solve it. And when we solve it, we get a, b, and c, and the partial fraction decomposition is finished. Do I feel like it? Perhaps not. Anyway, this is the multiply out and compare method. And you can also call it universal method, because this will always work for you. And therefore, this is the baseline method, the one which you can always fall on. But you pay for it by doing quite a lot of work. Now, fortunately, there are some alternatives which are shorter, but unfortunately, they are not reliable. So let me introduce some other possibilities how to obtain at least some of these values. Now, my personal favorite is something which I call hiding trick. Again, I'm afraid it doesn't have an official name, so let's stick with mine. What's A? Here is the hiding trick. I look below A and I see that this expression has root equal 1. So I take number 1 and I substitute it here. But first I have to hide. I have to hide x minus 1. I hide it, I substitute number 1, and I get minus 6 on the top. And I substitute number 1 here, and I get minus 2 here, which gives me 3. And that's actually the value for A. Let's try it again. For B, I can see here x minus 2, so I hide it. And the root is 2, so I'm substituting 2 into the remainder of this expression. On the top, 3 minus 18 is negative 15, and I divide it by 1 times 3 is 3, and the answer is negative 5. And finally, for C, I'm hiding x plus 1, so after substituting negative 1, I will get 12, divided by, and I'm substituting negative 1, so it's negative 2, negative 3, makes it plus 6, and C should be 2. And that's it. That was easy. I didn't even have to write anything. So when you want to use the hiding trick, you just move your finger a little bit around, you think for a few seconds, and you get the outcomes, you get the answers, which is very nice. By the way, these are exactly the same values which we would get over here by solving the system. Okay, let's try this one. A plus B plus C. How much is it? A plus B plus C is 0. Yeah, it fits. So that's my favorite. In this case, it worked perfectly. So if you want to see some examples where it fails, we'll have to wait for the next integral. Okay, that's hiding trick. There is another trick that I sometimes use, and I call it plug-in trick. It goes like that. You start here, you go here, but in this equation, you don't do any multiplying out. Instead, you put some number for x. How does it work? Well, what we really need is some equations. And this equality is supposed to work for all x's. So if I put some particular number into it, again, I get something which should work. Okay, let's try it. How about if I put x equal to 1, for instance? Well, on the left, I get negative 6. On the right, I get a times negative 2, so it's minus 2a. b times 0 and c times 0. So that's it. That's very nice. A is equal to negative 6 over negative 2, which is 3. And you can see that it's actually the same calculation that we did over here. And indeed, if you use the plug-in trick and you substitute one of the roots, it's exactly the same thing as if you're doing the hiding trick. So we didn't really earn or obtain anything new in this way. So perhaps we should try some other number. Not a root, but something else. How about 0? 0 is a nice number. So I put 0 on the left, and I get 3. And I put 0 for x over here, and I get negative 2a minus b plus 2c. Now, by a remarkable coincidence, it's exactly the same equation as here. And this is not an accident. When you are substituting 0 into such an equation, you will always get the equation coming from the absolute term. Now, when you have 3 unknown variables, you need 3 equations. So simply plug in 3 different numbers and you get 3 equations and you can solve them. So that's sort of a cheaper way to get a system of equations. If you are not lucky, you still have to solve it. But here we are actually quite lucky because we can get A, B, and C by smart choice. So that's the plug-in trick, and that's the basic try it for me. When I see a partial fraction decomposition, I usually first start with the hiding trick because it's the cheapest way to get some numbers. And if there are some numbers left which I cannot reach using the hiding trick, I try some other approaches. And now there is a fourth approach I want to talk about, and this one is sort of a bonus. Yeah, it's like a bonus for me. Sometimes I like to use it. We have this equality, which is supposed to be true everywhere. So in particle, I can send x to infinity. Now, if I do it, all these fractions will disappear. They will yield 0. So there is no information coming from it. So what I'm going to do, I'm going to take this equality and multiply it by a suitable power of x in such a way that at least one of these letters survives when I pass to infinity. Now, when we look at this fraction, we can see that multiplying by x is the right way to go. So I multiply by x everywhere. And now I send x to infinity. What do I get? On the left, polynomial of degree 2 is divided by polynomial of degree 3, so the outcome is 0. That's the limit on the left. On the right, all of these little fractions tend to 1. So I get a plus b plus c. And I get an equation almost for free. So that's something that I sometimes like to use. Actually, that's the same equation that we have here. So in this particular example, these alternative approaches didn't really bring anything new into the mix. But that's because this example is really exceptionally nice. So to see how these additional methods can help us, we have to look at examples which are a little bit less nice, but not too bad, don't worry. So here we have another nice looking ratio of polynomials. So let's apply the partial fractions decomposition. And again, we got lucky, and the denominator is already prepared. We can see the factors, and thus we can write. The first partial fraction is determined by x plus 1, and the second by x minus 1. However, now the factor x minus 1 is raised to some power, and there is a rule which says that we should increase power here step by step from 1 to 2, then to 3, and so on, until we reach this particular power. In this case, this will be very short. From the first power, we jump to the second one, and we have a match. So that's the end of the story. So that's the basic setup for this particular ratio of polynomials. Again, we have to determine a, b, and c. And we start with my favorite, the hiding trick. So let's have a look at it. We are going for a. The root is -1, and I'm hiding x plus 1. So I'm putting -1 here. I get -2 squared is 4. And in the numerator, -1, -3 is -4. And a is -1. Very nice. Okay, let's try c. I can see x minus 1 squared. So that's what I'm hiding, x minus 1 squared. And I'm substituting 1 into the remaining part. So I'm substituting 1, and I'm getting negative 2 divided by 2. The answer is negative 1. That was also nice. How about b? I can see x minus 1. So I'm hiding x minus 1, but notice that it's here with square power. So when I hide x minus 1, I'm essentially hiding the power, and there is still the x minus 1 factor left. And now I'm supposed to substitute number 1, but it's not possible. Division by 0 problem. So this tells us that the hiding trick cannot determine b. And that's one of the drawbacks of this method. Unfortunately, when you have a linear factor with higher power, the hiding trick only helps you with the highest power here. It doesn't help you with the lower powers. So that's about as far as the hiding trick gets us. We still have one letter to determine, and essentially we have to go to the universal method, but perhaps we can stop earlier. We will see. Anyway, let's write down what we want. X minus 3 over x plus 1 times x minus 1 squared should be, and I'm going to incorporate the results which are already received. So a is negative 1 over x plus 1, then there is b over x minus 1, and finally there is negative 1 over x minus 1 squared. Now if I want to use the universal method all the way through, I would have to multiply by the common denominator, and I get minus x minus 1 squared plus b x plus 1 times x minus 1, and then there is minus x plus 1. And now I would multiply out, compare, and I would get essentially just one equation is enough. See, there is just one unknown letter. So I'm really looking for just one equation. So perhaps I could skip this multiplying out business and comparison, and I could try my other tricks. How about a plug-in trick? I look at this equation, and when I substitute x equal 0 into it, which is not a root, so I'm not really messing up with this hiding trick, that will be a new information, I get negative 3 is equal to 0 here is 1 squared, so it's negative 1. 0 here, it's minus b, and 0 here is minus 1. Let's have a look at it. I take b and I move it to the left, and I take negative 3, move it to the right, something cancels, and I get 1. Voila! b is equal to 1. We are done. Wonderful. Okay, how about the fourth alternative that I talked about earlier, the limit trick? Well, I would really love to see some information about b. And if I want to see information about b, I would like this fraction to go to 1 at infinity. So I'm going to multiply everything by x. Here we go. And now I send x to infinity. What do I get on the left? Degree 2, degree 3, so this goes to 0. And on the right, this goes to 1. This goes to 1. And this baby goes to 0. And we have a nice equation, which leads to b equal to 1. Perfect. So that's the end. We have a confirmation. And that's the end of the partial fractions decomposition. Now, perhaps we could actually finish one of these problems. Let's have a look at it. Let's write it in a nice way. I see integral negative 1 over x plus 1 plus 1 over x minus 1 minus 1 over x minus 1 squared dx. And we will make some room. Now, an experienced integrator would look at it and say, wow, these are elementary integrals, and write the answer right away. But perhaps we are not that experienced yet, so let's have a look at it. First of all, I'm going to split it into 3 integrals, because integration is a linear operation. And I get, okay, I will factor minus. So it's minus integral dx over x plus 1 plus integral dx over x minus 1 minus integral dx over x minus 1 squared. And these are really standard cases, and one should know them. One should know how to approach them. These are all problems that can be handled easily using a substitution. Now, we will have a video on substitution, but I'm assuming that you know at least some basics. So let's go for it. Here I'm going to call x plus 1 by the letter u. Here I'm going to call x minus 1 by the letter v, and that's actually it, because I will use the same substitution here. Now we have to work out the transformation for differentials, but in this case it's very simple. So there will be no change in differential, essentially. No extra constant or anything like that. These are shift substitutions, the best substitutions you can get. And that's why experienced integrators would do them just in their head. Shouldn't forget about minus here. Okay, the first substitution leads to du over u. The second one gives me dv over v. And the last one, okay, I'll look a little bit ahead. We don't have a rule for 1 over v squared, so I'm going to write it as a power. So this will be v to negative 2 dv. And these are elementary integrals. Let's go. Minus logarithm u plus logarithm v minus v to negative 1 over negative 1 plus c. Shouldn't forget plus c. And finally, and by the way, this is a different c than this one. It's not all that nice, but that's how people do it. So let's not worry about it too much. Now we have to use back substitution, and we have minus logarithm x plus 1 plus logarithm x minus 1 plus 1 over x minus 1 plus c. Wonderful. If you feel like it, you can connect these two. So you can write it as logarithm x minus 1 over x plus 1 plus 1 over x minus 1 plus c. And this is important, where is it valid? Let's have a look here. 1, negative 1. These are bad. So let's ban them. And that would be the answer. It's important not to forget the absolute value in the logarithm. Otherwise, we would restrict the region of validity. Here we have our last integral, and we can see something new there. There is an irreducible quadratic factor. Of course, we should know how to handle such a case. So let's start with the general setup. We have a linear factor here, so that's quite obvious how to react to it. We get a partial fraction. Then there is another factor. One factor means one partial fraction, because it's not taken to some power. And here is the new part. When you can see a quadratic factor as the basis, we have to put a linear factor on the top. That's a general rule. Now, if this quadratic factor was squared, we would add another fraction where this would be squared, and on the top there would be a linear factor again. Okay, that's the general rule for that. Anyway, we have our partial fraction decomposition, and now it's just a question of finding a, b, and c, so let's try it. My favorite hiding trick. To get a, I cover x minus 1 and substitute the root. And I get, okay, let me put it here. I put 1 into the numerator and I get 3 minus 2 plus 1, looks like 2. And here, after hiding x minus 1, I substituting, I get 2. So a is equal to 1. That's nice. The second part. Well, that's a good question. If I hide x squared plus 1, do I get b or c? Actually, I don't get anything because this doesn't have real roots. I could try to substitute I and minus I, the complex unit, but it's not a good idea. Trust me on that one. So that's the end of the road for the hiding trick. So we see the second limitation. We already saw that the hiding trick does not really handle well if the linear factors are taken to some power. But it also cannot help us with quadratic factors. For that, you have to go to the universal trick or to some of the other alternatives. Let's have a look at it. 3x squared minus 2x plus 1 divided by x minus 1 times x squared plus 1 should be equal, and now we know that a is 1, plus bx plus c over x squared plus 1. And now we should multiply by the common denominator, multiply out, compare, and we would get b and c. If we feel like it. That's the beauty of the universal method. It always works. Let's try some alternatives. How about the limit trick? I actually quite like it, so let's enjoy it here. Let's say that I want b. If I want b, I would really appreciate to have a square polynomial in the numerator, because then by passing to infinity, b would jump out. Can I achieve it? Well, I would have to multiply all terms by x. And will I get something nice? Well, if I multiply everything by x, here I will get limit 1, and here it will be polynomial of degree 3 divided by polynomial of degree 3. This is not a problem. Let's do it. So I get 3x cubed minus 2x squared plus x divided by, I will multiply it out, x cubed minus x squared plus x minus 1. In this way I will see how the polynomials look like, and I can take the limit easily. Okay, here we get x over x minus 1, and here we get bx squared plus cx over x squared plus 1. Now we send x to infinity. When I do it, on the left, the highest power determines the outcome, and I get 3. On the right, this tends to 1, and here this tends to b. And I see that b is equal to 2. Wonderful. So we avoided the tedious multiplying out work. Okay, what next? Well, I would appreciate if I could get c, but to get c I would have to multiply this original equality by x squared. And if I do it, this term will blow out. It will go to infinity. Now, this can be actually salvaged, because now we know b is 2, so I could move all the terms to the left, and yeah, it looks like work, so let's not go this way. Usually I just get one letter out of this limit trick. So probably I have to, well, get rid of the fraction here. Let's make the next step in the universal approach and see what we get. After I multiply, x minus 1 cancels. And now I know that b is equal to 2, so it's 2x plus c multiplied by x minus 1. Well, do I feel like finishing this approach? Actually, no. I'm going to use the plug-in trick. What happens if x is equal to something nice? Let's say 0. When x is 0, on the left I can see number 1. On the right I can see 1. I can see c. And I'm multiplying by negative 1. Now 1 cancels. And I get minus c is equal to 0, c is 0. This concludes the partial fractions decomposition. Let me just write it nicely. So my integral is of 1 over x minus 1. Let's split it into two integrals. dx over x minus 1 plus integral 2x over x squared plus 1 dx. And let's finish it. Okay, the first integral, we had one like that before. This is done by easy shift substitution. So an experienced integrator would just write down the answer. It's a logarithm of x minus 1 in absolute value. Let's have a look at this one. Well, why don't we apply partial fractions decomposition? It's a ratio of polynomials. Well, if we do it, we end up with the same ratio, because this is a partial fraction. So of course, if you want to use the partial fraction decomposition as a method of integration, you should know how to handle the partial fractions which you obtain. And for this one, there is a standard approach using substitution. You take the denominator and you assign it a name. Well, let's make it here. Let's say u is equal to x squared plus 1, then du is 2x dx. And by a remarkable coincidence, this exactly fits my integral. Actually, I set it up that way. Anyway, after I do this, I get integral du over u, which is a very simple integration. Notice that I didn't write any plus c here because it's still hidden here. This already includes plus c, so I don't have to write it. But now there is no integral anymore, so I have to write plus c. And finally, after the back substitution, I get logarithm of x squared plus 1 plus c. And what's the condition on existence? X should be different from 1. That's it. So, when you think about it, every kind of expression which appears here, we should be able to integrate. The expressions which are based on linear factors, they are simple. We saw it in the previous example. You just used linear substitution and everything worked fine. So what we really need to know is the following two types. Ax over x squared plus, let's say, b dx. And these are handled using substitution. U is equal to x squared plus b. And this can be always worked out. Very easy. The second possibility, or the second type, the second quadratic type, happens when c is not 0, because then there will be another term. And they cannot be handled together. I cannot integrate it as a whole unit. So we have to separate it, and we would have something c divided by x squared plus b dx. And now it depends on your teacher, essentially, which approach is taken here. You can either memorize the outcome or you can get a procedure for it. But I can tell you the main approach is based on the following. If there is 1 here, this is simply c times arctangent x. And c is not a good constant here. Let's make it into a d, because there will be plus c and so on. Okay? So these two approaches should be known if you want to integrate using partial fractions efficiently. And that's about it. So, see you in the next video. Well, hello again. I have been editing this video and I realized that there is something that I didn't say, and you probably know it, but it should be said because it's important. In those 3 examples that we did, all the rational functions were proper, which means that the degrees of the polynomials on the top were always smaller than the degrees in the denominator. And when you have a proper rational function, you can apply partial fractions decomposition. However, there are also other rational functions. For instance, this one. On the top, degree is 3. On the bottom, it's 2. Unfortunately, 2 is not more than 3. So we cannot apply partial fractions decomposition yet. Instead, we have to recall the long division. Let's have a look at it. It's long, but it's life. 4x cubed minus 2x squared minus 4x plus 3 should be divided by x squared minus 1. We divide the highest powers, we get 4x, and now we find the remainder. So I multiply again, and I get 4x cubed minus 4x, which fits here. How much is left? This cancels, there is minus 2x squared, this cancels, plus 3. And we recycle it. Okay, minus 2x squared divided by x squared is minus 2. We find the remainder. I multiply, I get minus 2x squared plus 2. And how much is left? 1. Because the degree of 1 as a polynomial is smaller than the degree of the divisor, this is the end of the road, and we can take the answer and put it into our integral. So we are in fact integrating this 4x minus 2 and the remainder, which is 1 over x squared minus 1 dx. So the long division takes your rational function and changes it into a polynomial, which is easy to integrate, and a proper rational function. So right now we can apply the partial fractions decomposition, and the rest of the problem is easy. If you try it, you should get this result. And that's really it for this video. See you.